Log on, tune in, find out. Another good idea from Cambridge.
Today there are two lectures, and the first speaker is Professor Maciej Niespolski from Moscow. Warsaw. I'm sorry.
Very close.
From Warsaw, and yeah. So he speaks on the title you see there.
Yes. Opposite to former speakers, I wouldn't like to thank organizer directly. I would like to thank all of you for the moments of illumination I experienced during last month. But of course, it wouldn't have happened without organizers. So thank you all. And yes, this is the title, a bit lengthy. So you don't find any new idea in the talk. More of the ideas are 100 years old or even older. And then some new things appear, and they're not quite fresh, new. They just appeared between two events in Cambridge. So this is more or less the period of 9 years that we discovered. Yes, I think this just quite basic talk will help you in your okay. I think we have to sometimes stop for a moment and look at the past. So the object, main object is the second order differential equation, two-dimensional one, linear. So just comments on notation. So everything you can see are functions of two independent variables. So A, B, C, and so on are functions of x and y. And phi is given function, and phi is dependent variable. Yes, psi. Yes, and during next 50 minutes or less, I'm going to talk about this object, or discretization of this object, a particular one. But not only about the object, but also some subclasses. So we have the class of equations, and then we have also some subclasses. Yes. So for instance, we can demand this equation to be self-adjoint. This is the first thing. So we are demanding something. I will be back to the subject later. Then we can change independent variables as well. So in the continuous case, we have the freedom of changing independent variables. Yes, I would like to address. I would just refer to this procedure as specification, because in the discrete case we don't have this property, and moreover we can gain also from this new word. And so this is just, if the operator is hyperbolic, this is just canonical form of the operator. Yes. Then of course we have you can do something more. We have gauge transformation. So we can always change operator by multiplying it from the left and are just operators by multiplying by a scalar function. Yes, so yeah, and then psi is equal psi over theta. Yes, so we have some subclasses of the equations. And then I can show you more just briefly, because I will back to the point in a moment. You can see this is just hyperbolic second order differential equation in two variables, and here you have some special cases. So just by brute force you have some subcases. But what is the main point? That all these classes or subclasses are covariant under a vast number of transformations, which we call today Darboux transformations. And the idea is to, in the discretization, to preserve this property. Yes, so, and the top is from the very beginning thought as a tribute to the people who lived 100 years ago or even more. So you can see, because this sort of Darboux transformation, so this type of Darboux transformation is today very old. It's the names, for instance, for this equation, we have so-called Jonas fundamental transformation. For this equation, this is perhaps the first Darboux transformation we ever knew. It's Mutter transformation. Then we have, for this class of equation, we have Gursat transformation, and there are some miracles behind this, because perhaps it was Darboux who was the first. Then we treat this phi as a multi-component vector, so and we demand that R lies on the quadric. And the point is that I don't want to say that it's a sort of classification, but it's sort of complete list we know. And the other cases can be reduced to this. We know it can be reduced to this. Let's say 4, 1, 2, 3, 4, because the two are related. So I will concentrate mainly on these first two. I briefly mention the Gursat case. Then we can discuss, because later. Yes, because I'm talking about the linear operators, but in fact, behind there are nonlinear systems, and we have several classical methods to obtain some nonlinear system associated with a given operator. I just give you two examples, though. So with the, for instance, with the Mutter operator, it's associated the hierarchy of nonlinear equation, which we call Nizhny-Kieslov-Novikov hierarchy. And you can see here, so we often refer to this first equation. So this is the Laxper for the, so you are experts. So we add the second operator to the given operator, and then we find compatibility conditions. And you can see compatibility conditions. This operator is in this case just a third order operator of in the variables u and v. So that's how we find it. So behind this operator you can find the whole hierarchy of the nonlinear equations. But there are some other methods to produce nonlinear systems. So, and this is perhaps the most classical one. This is the Bianchi system. You can find it in the literature, the very old one. and Bianchi gave the backroom transformation for the system. So this equation is constrained. So now we demand that n-dimensional vector satisfy this constraint. Yes, I will back to the. Yeah. So I will start from the very basic things, from the mutar transformation in the continuous case, because I think that the most important is our next few minutes that to grasp the main idea behind. So I'm going to derive the Darboux transformation or mutar transformation for this two-dimensional Schrödinger operator. And it's quite easy. So you can think about the psi as a solution space of the operator or vector infinite vector. Yes, then you choose one element of the solution space, a solution of the equation. And then what you can do, you can eliminate function f. I just eliminated function f. So then some simple exercise from the differential calculus that you can do it in this form. So you have the divergence of a vector of something is vanishing. So we can introduce potential. It should be tilde, not bar. It's just tilde. It's a new variable. This is new potential. And then we have so then we have this sort of transformation, and I just rewritten these two equations. Yes, and you can see the invariance, because when you change theta over 1 over theta, nothing will change. That means that this psi bar, I don't know what is going on, but it should be psi tilde. This psi bar satisfy a new equation, but of the same type. Yes, but the only difference is that the potential here is different. So we have covariance property of the operator. And this is exactly mutar transformation for this operator. So you have this solution space of the one equation. You choose a particular solution, and it defines you through this transformation a new object, psi tilde, which again satisfies the same equation but a different function f. And this is very classical result, but for the mutar transformation, we have the same sort of transformation, so you can see the difference. And from these two examples, and nothing will change in the derivation. And you can repeat the procedure in the general self-adjoint case. So this is self-adjoint equation. I'll be back to the moment in a moment. And here you can see so you are taking the solution of the equation. Solution, yes, so you're taking solution, theta, and here you can see the transformation. So I still would like to refer to this sort of transformation as a mutar transformation, because essentially the transformation is the same.
So in this case, the A, B, and C remain the same, but F changes. Is that right?
No, there are. You see, there are small. In this particular case, perhaps yes. In the continuous case, yes, because you have to invert. You have to invert matrix. So there is maybe I'm not sure. Yes, but perhaps there is a small change multiplying by theta over theta. Yes. Yes, but definitely. Okay, the discrete case is more complicated, so we'll see in a moment. But definitely, a tilde is proportional to a through the sum factor. Yes, and yes, so in fact, what is really important that what can help us is the formal adjoint operator. Yes, because because what essentially we did, we had this structure that you have operator acting or on psi theta. Yes, psi and theta, and it was equal to 0. Yes, and we know that it can be written u plus x, say plus y. So this is just, sorry, maybe I will go faster. Because this is some derivation for the students, let's say. So, so this is more as the structure. Yes, that we define formal adjoint as by integrating by not integrating, just using the Leibniz formula. And usually we are hiding something under the carpet. But in this moment, for us, it is important that this thing is equal to 0, so we can introduce potentials here. Yes. So we have divergence of something is equal to 0, and this is the main idea behind the story. So now we are going to the discrete case, and I have some maybe not usual notation, but which is very useful in higher dimensions. So from now on, the forward shift operator I will denote just by subscript 1. Yes, in the first variables. When I am talking about the forward forward shift operator in the second direction, I just add subscript 2. And similar things for the backward shift operators. Yes, and here you have some examples. So I'm never going to use this complicated object, but still just to show you some examples. And then I'm going to use the forward difference operators and backward difference operators. Yes. So then there is a story about finding formal adjoint in the discrete case. Yes. So again, the same story. We are shifting the operator. For instance, shift in the first, shift in the second direction. We are shifting it on the second operator, on the phi function. So, oops. And then we obtain a formal adjoint to this operator. Yes. So just standard things. And to start with, we have some. We pick up some self-adjoint operators. So this is. I will show it in a moment, but Novikov considered Laplace transformation for the self-adjoint 7-point scheme. So this I will show it in a moment. So this is a scheme that relates 7 points on the triangular lattice, because it is better to take a look on a triangular lattice. But the description is still Z2 description. So this is the second direction, and this is the first direction. Yes, and here you have point -1, 2. You may have experience with the Laplace transformations and Darboux transformations for one-dimensional Schrödinger operators, where these two things more or less coincide. So in the so for the one-dimensional Schrödinger operator, Darboux transformations and Laplace transformations are more or less the same. You have to be a bit. You have to take care of the intrinsic spectral parameter. Whereas in the two-dimensional case, when you have two-dimensional Schrödinger operator, for instance, it doesn't work. It is completely different story. So Laplace transformations are not Darboux transformations. Maybe some degenerate case of the Darboux transformations, because as we know, Laplace transformations is just, if you have given equation, second order equation, Laplace transformation has two Laplace transform, up and down, and nothing else. Whereas we have plenty of Darboux transformations. So we can repeat. So this is the operator. This introduced by self-adjoint operator on a triangular lattice, which relates 7 points. And we do exactly what we did before. So we have a solution space of the operator. We fix one particular solution. We use this property because operator is self-adjoint. So divergence of the vector vanish, and we can introduce new potential. It is exactly the same transformation as we had before for in the continuous case.
Sorry, Maciek, maybe I missed it, but why you say that this is on the three-dimensional lattice?
It's not on the three-dimensional
Triangular
lattice.
lattice.
It's at a triangular
triangular
lattice. Triangular lattice. I said three-dimensional. Okay.
No, sorry. Why is it?
No, not three-dimensional. Triangular lattice.
But why?
Sorry.
Why?
But why? Because of some. Okay, it will appear in a moment when I present some moment. Because then.
Because just if you write it like this,
yes, then you can always think that it's just typical quadrilateral lattice. Let's say square lattice. Yes, and just yes, and to kick it or not to kick it's your choice. Yes. Yes, but then I will back to the question. Yes. And you see, what can you do in this discrete case? We can always put c equal to 0, and then you end up with this 5-point operator. So in the continuous case, it corresponds to the change of the independent variables. So or just you can kill this coefficient c equal to 0. But of course, in the discrete case, you cannot kill a and b equal. You cannot put a and b equal 0, because then this operator is too degenerated. You have an operator which relates 3 points. It can't be related as discretization of the second order differential equation. So that's why you can put a and b equals 0 here, whereas you cannot do it here. So we need some different things, and I will back to the point in a moment. Yes, and that's why I would like to call this operator, because the transformation doesn't change. So this is the Feynman scheme. Now it's on the square lattice, and this is just the transformation, still similar to the previous one. Okay, so now we are going to generalize slightly. Because so far we were talking about this picture. You had operator which was self-adjoint. Now we are going to the case where operator is not self-adjoint, and there is a small problem because this procedure I told you works, provided in the continuous case, provided this function f is equal to 0. But this is not the real problem, because we can always transform this equation to the form f equals 0 with particular gauge. We are choosing, we divide the psi by the solution of the equation itself. And then we get operator which is exactly in this form when f is equal to 0. And we refer to such a transformation as to such a gauge, as an affine gauge, when the last term disappears. Yes, and this gives you the idea to present something new, because perhaps the main idea, also the next idea, is to when you have such a transformation, you can easily deal with the inverting of this transformation, because we are able to invert 2 by 2 matrices. So we know if psi tilde satisfies an equation, psi tilde should satisfy the same equation if there are no constraints on alpha, delta, alpha, beta, gamma, delta. Yes. So we can calculate the compatibility conditions. Yes, and then you end up with a. I will say something very important in the previous case. Sorry, I will back. I completely forgotten about it, because there is a very important thing. You can see forward difference operator here, whereas here is backward difference operator. Yes, so so it's slightly different. Now, whereas now we are going to the point when here and here you have forward difference operators. And you can see when you find compatibility condition for this system on phi or on psi tilde, then you end up with a linear equation that relates 6 points. Again, you can't see why it's on the triangular lattice, but in a moment maybe it will become clear. And as you can see, there are 4 coefficients: alpha, beta, gamma, delta. Yes, and the question is, can you transform somehow this? If you take the general 6-point scheme that relates linear scheme that relates 6 points, can you transform these equations somehow to this to this special equation? And can you do it by means of the gauge transformation? And the answer is positive. Yes, you can always do this transformation. So you can always go from this operator to this operator by gauge transformation. So by this transformation, but provided that theta is solution of the, so you multiply from the right the operator by theta, which is solution of the equation, and from the left by phi, which is solution of the adjoint equation. And you end up with, so it turns this operator into this operator, and then you can write such a such transformation. There exists such function psi tilde, and this transformation from psi to psi tilde is when you have two parameters, let's say, two functional parameters. One is the solution of the equation, and the second is the solution of the adjoint equation. You have a transformation which maps from the psi to psi tilde, get this formula. And this is nothing but the Jonas fundamental transformation for the 6-point scheme. Sorry.
Excuse me, psi tilde is the solution of the first equation, 6-point scheme?
No. Theta is solution of this equation. Yes, the general one. Yes. Whereas this object is satisfy the adjoint equation to this equation. Yes.
Psi tilde, you find what?
Psi tilde is satisfied 6-point equation as well, but a different one with different coefficients. And now I'm going to show you the transformation rules for the coefficients. Yes, because this is the object, and the new fields, because psi tilde satisfies the same equation, but with the new coefficients. And now some explanation why I'm using the triangular lattice. Because you can see that transformation rules for A, B, and F are similar. So you have some, so this transformation does not distinguish the outer corners of the triangle. If you have 6 points, so these points, the coefficients at these points transform in a very similar way. So in principle, what you can do, for instance, you can kill both of them, A and B. So then these terms drop out, and we have quadrilateral, let's say, or 4-point equation, which I will discuss in a moment. But you can kill all these terms, A, B, and F, and then you end up with something on the triangular lattice, on 3-point scheme. And I think perhaps most of you are familiar with the Larkspur for the Toda Miwa equation, Hirota Miwa equation, and
Do you mean that choice is permitted because of the structure of the transformation?
yes, this choice is permitted because
Darboux transformation preserves that structure.
yes, because if you kill A, then A tilde is 0, and you can kill all the 3 things. And the point is the transformation preserved the structure, and this is, but still it's the same transformation. Essentially, you have the structure that you have take solution of the adjoint equation and do the transformation. Nothing changed. It's not the. I wouldn't like to call it reduction. Reduction is something that imposes constraints. Yes, let's page up maybe. Impose constraints on these data. So, for instance, in the self-adjoint case, you have to have psi tilde is phi is equal to theta exactly, but it's not the problem because yeah. So because it's self-adjoint equation. Yeah. I am missing something at the moment. Yes. So to complete pictures, okay. So that's what I thought. Yes, that you have some gradation. So you have 6-point scheme, you have specification the 4-point scheme, and then specification the 3-point scheme, and you can do these things also in the continuous case. Then you can also choose the gauge, because arbitrarily as you want. So there are the standard things is when you have these two forms, you can always kill f equal to 0. Or in the discrete case, say that the sum of the coefficients equal to f, and we call it gauge, affine gauge. And then in this case, constant satisfy the equation. Then you have the freedom of the farthest specialization, and you can set these relations to be valid, and nothing is lost. So you can always do it. It's not important in the transformation, because the way you are writing gauge is something that is not important. Yes. Yes. So now I'm going to the 4-point scheme, because it's the most studied scheme. Yes. And then we have this old concept of Laplace invariance that under the gauge. So now I am demanding that here C is equal to 1, or 1/2. So this coefficient is equal to 1. So I have this sort of the gauge. And I am going to talk, but then we have some invariance of the gauge. So you can build out of the functions something which is invariant under the gauge, and it defines you the equivalence classes of the gauge. And in the fact, we are always talking about the equivalence classes of the equivalence classes of the gauge. So yes, and then there is some result that we have Mutter equation, and we have discrete Mutter equation in the discrete case. So you can see it's quite odd result, and this is the example of the equation that also admits Darboux transformation. And again, the procedure of deriving it is the same. You have function f, you eliminate f, and you obtain something. You obtain this sort of transformation, which preserves the form of the operator. But there is small thing. Okay, maybe I have to add something more, because then you can change a gauge. You can introduce minus here, and in the transformation you have plus here. This is really amazing story, because this doesn't exist in the continuous case. This is what this person knew it very well, perhaps, that you can have plenty of copies of this equation when there is a minus, and you can have compatibility conditions, and you have just in the Darboux transformation you have the row of this sort of the equation of the transformation. So, and it works in n component case, whereas in the continuous case we have only one component.
What are kappa and n?
Kappa and n okay. This Laplace invariance. So this is just definition of. Oops, I not this way. These are invariance of the Laplace invariance of the gauge transformation. So this is invariant characterization of the Mutter equation. This equation is written in a specific gauge. Yes, then you can choose a gauge. You can change the gauge, and it is still the Mutter equation, but in disguise. Yes, because you are quite familiar perhaps with you prefer minus here. Yeah. Yes, but it's just simple gauge. You multiply by the minus 1 to the power n. And yeah, and this is another story, yes, because we can introduce minus here because this equation has a proper continuous limit. This is the case when you write it like that. It goes to the mutar equation. You can introduce minus here, but then the limit is completely different. You have first order. This becomes first order. That is very nice because, again, because you have complex analysis and you have a specialist here. So with a special choice of f, of course. But still you have Cauchy-Riemann. This can be interpreted as Cauchy-Riemann equations. It's also, thank you. It's, yeah, it's a very important thing. Yes, but surprise, because the equation is not self-adjoint. Mutar equation in the continuous case is self-adjoint, but whereas in this case it's a bit different equation. Adjoint of the previous, or of the mutar equation, is this equation. And of course there is some, it's standard story in the discrete case, because usually equations on the quadrilateral case, when you have 4 points, that they come in pairs. So the solution space of the two equations, if you have a solution of this equation, mutar equation, then you can find a solution of the adjoint equation. So it's x1 plus x2. So it's a sort of potential version. Yes, but it's very typical story in the discrete case. Yes, that equations are not self-adjoint. Yeah. Yeah, and this equation has also some geometrical applications. Yes, and now another story. No, I am afraid to, because it is a quite classical story in the statistical mechanics or in the business with complex analysis, discretization of complex analysis, that we can go from the discrete mutar equation to the 7-point scheme. So to do that, you have to consider the planar situation. So you have some tiling of the plane. And what you can see that on every placket of the of every quadrilateral, you have the mutar equation. Yes, and the point is what is very specific for the mutar equation, that it's the only scheme that up to the gauge transformation that allows for this elimination. So this is just to show that this is just mutar equation on every quadrilateral. Then you just add minuses and subtract, and you end up only with equation on the 7 point on the black points. So I will show the picture once more. So you can eliminate these white points, and you have relationship between 7 points. And this again, this is exactly the 7-point scheme I showed you at the very beginning. Still, you have to remember that we have some freedom of changing the gauge. The 7-point scheme. Yes. Then what you can do, you can say that okay, let's take the equation, eliminate points around the white point. So you can eliminate black points from the equation. If you take this point and you go around this white point, you can eliminate these 3 points, and you obtain some linear problem on the hexagonal lattice, because when you can see the structure of the honeycomb here. Yes, white points constitute the honeycomb lattice. And to end this picture, I will just show you, yes, because I am running gently out of time. You can see that already this self-adjoint case is quite complicated, but very nice. You have discrete mutar equation, which is basic one, let's say. Then you have the discrete mutar equation. adjoint, of course, should be added adjoint. Adjoint of this equation. Then from this equation you can derive the 7-point scheme or its restricted version, 5-point scheme. And then you have some also linear system for the honeycomb lattice. I can tell you about it later on, perhaps. And the point is, very important thing is that this elimination procedure, the Darboux transformation can be derived from this fundamental one. That from perhaps Miwa was the first who, or maybe I don't know who was the first this transformation, but from this original, all the other can be derived by eliminating. So not only on the level of the equation itself you have this elimination procedure, but you can also do it on the level of the Darboux transformation. So you can derive the Darboux transformation, and that's how the Darboux transformation for this scheme appeared. There are, okay, so perhaps I have to skip because there are some, this is just for the 5-point scheme again, but with more symmetric form. It's nothing new here. So you can have this sort of schemes. So some tricks in the discrete case you can play with. And then you can do these strange tricks with the 7-point scheme, so double the situation, and you still have 10-point scheme. So referee asked me to remove, of one journal asked me to remove this scheme because it's so worth 9, not 10 points, what for? But I have some argumentation because I haven't talked about the boundary problem. So the 7-point scheme is good. It's very good to solve some Dirichlet problems. Whereas this one is perfect for some evolution problems. So you have some hyperbolic type problem, and so initial conditions and then boundary conditions, but then we can also discuss it perhaps later. So this is the Darboux transformation. Yes, and then just I want to mention, so because this is amazing stuff, because this is the story about the discrete Gursa equation. So it's a different story, and my idea is to write it in the form that Gursa did. So it's 109 years ago, and this is the discrete version. Perhaps it was given. So it's still a priority. Perhaps gives to Wolfgang Schiff or D'Oliva and Santini. And there's some controversy. Yes. So you have some Gursa equation, and this again there is a Darboux transformation. I don't want to show it. And some applications. So again, some example of the. So you have Bianchi system. Then we have discretization of the nonlinear system. So this is called collapsal equation by Wolfgang Schiff. And then we have some sort of potential version. No, this is potential version. And we have some another equation which is related to this one by this. Which is, the one is related with the Mutter equation, and the second is adjoint Mutter equation in a different gauge. So you can compare these two equations. So I think they are both important. So yes, we call then this one discrete hyperbolic Ernst equation. But I don't. It's the proper. Yeah, yes. Then another story is you know this is the 7-point scheme. And now I call this -1, 2. This is. I am back into the question of Frank. Why I need triangular lattice? Because then the formula looks better, and this can be treated as a just shift in the third direction, No, not, it's still situation is planar, because we assume we are on the triangular lattice. This shift is related to -2 and -1, and these formula are very nice. This is the only argument I can give you, because otherwise you can have to add -2, -1, something like that. But the situation is completely, the point are symmetries. The situation is completely symmetric with respect all directions. That's why I want to keep triangular lattice, because this is the Laxper for a system I am going to show you now. Oh, very complicated. So this is just nonlinear equation, so plenty of things to be done. Let me kill, because I am in I can easily go from the 7 point to the 5 point. Let me kill C to do it properly. And this is the Darboux. I killed the C. This is the Darboux-Beckmann transformation for the nonlinear system. You have this is just the, let's say, Mutar transformation. This is time transformation for this object. And you demand that this K must obey this constraint. And then we obtain new solutions of this nonlinear. We obtain this is nonlinear system. We obtain new solutions of the nonlinear system. These are just new solutions of the nonlinear system. So this is standard thing. Yes, and the form of the equation in the bilinear form. Yes, so because this equation can be written in the bilinear. No, it's not bilinear. It's quartic. Yes, but still with the tau function. Yes, in this nice form, where W is the just Wronskian of this. So of this, it's Wronskian when there are with two variables. Yes. Yes, and yes, I think I wanted to talk a bit about the multi-component, yes, several copies of this equation, so multidimensional scheme. That just tell you simple things that we know that with the 3-point scheme is related Toda, discrete Toda, or let's say Hirota-Miwa equation. With the Mutar equation, discrete Mutar equation, we have it's related Miwa hierarchy. Yes, so with the 3-point scheme, let's say Hirota-Miwa, with the Mutar Miwa, then we can have CKP, which is related to the discrete Gursa. So we take copies of the Gursa equation. This is the CKP. But then we have a more general scheme. So this system, yes, this is just for the arbitrary quadrilateral case. You have this system of equations when tau ij are functions. This has nothing to do. These are shifts in the ith direction, and you have tji, which are just another tau function. So you have system of equation on the tau function. Yes, but then we can discuss it later, because I think this is the end in Polish.
Are there any questions?
This bilinear equation, which wasn't.
Sorry, which wasn't.
Which wasn't bilinear.
Yes, it should.
So what is the effect on the tau function of the Darboux transformation? Is it simple? Or I mean,
yes, I don't know. Yes,
No.
No, I don't know. Yes, what is the transformation?
well, often it's just a multiplication of the tau function by some eigenfunction or eigenfunction potential or something. Is it as simple as that or not?
I don't know. Yes, yes, but it's a good question, yes. Yeah.
To what extent can the emergence of all these transformations be seen as a factorization problem of the linear?
Nothing to do with the factorization.
That's the message that we got from Novikov's talk.
No, that's not true. Thank you for the question. No. Because I mentioned this is a very important thing, because what you get from the factorization, you have the Laplace transformation. And then in two dimension, it's a very rigid situation. You have two transforms. You have up, you have one up and one down. And this is the Laplace transformation in the two-dimensional case. You have just chain of, you have initial equation and then you have chain of equations. Yes, very fixed chain, no freedom at all. Whereas when you have Darboux transformation, you have freedom of choosing of the solution. So this is a completely different story. These Darboux transformation are just vast number of the transformations of the operator. Yes, because you have freedom of choosing the solution. And solution, if you have second order differential equation, you have plenty of solutions. You agree? Yes. So then when you go to the when you do a simulator reduction, you are losing everything. You have to introduce. You have to remember about introducing spectral parameter. Otherwise, you are cooked.
So we don't have time now. So let's thank the speaker again.